Hello everyone. Today we're going to take a look at a very important type of function that will actually take us one step further in getting a complete handle on this area problem. And those functions are called area functions. So what we're going to do is define what an area function is, get some intuitive understanding of what they do, maybe compute an actual area function, show you how you can use it, and then illustrate the most important sort of calculus property of these area functions to kind of set the stage for a proof of a more general and an extremely important theorem in subsequent videos. So we're getting to that point where it's like we're climbing a mountain and we're almost at the apex, but we still have to do a little bit of heavy lifting. Okay, so let's kind of set the stage. Now, with the area functions, one thing that is sometimes a little perplexing for some students is that the area function is making reference to two variables, right? So it's not just an x, you might see a different variable as well. So let me try to explain how that works. So let y equals f of t be continuous on the interval, and let's say the interval, now what I'll do is I'll use the inequality notation for the interval just so that it's clear. So we're using t as the independent variable of our function, and the interval will be from a fixed number a but to a variable x, right? So a is some constant, some real constant, and then x is a real variable, right? So let me kind of sketch what one of these functions might look like. And to make it as general as possible, so I am going to, let's say this is a, and here is my function, something like that. This is y equals f of t. So just, in fact, let me go ahead and extend the horizontal axis all the way out. Let's do this. So that means this is your t-axis, and then this is your y-axis. So y is a function of t. Here is that fixed constant a, and then I'm going to indicate what what role does this variable x play? Well, x represents the upper limit, right, and or the upper the upper limit on the region. And then as far as the area, it would be this net area. So there, and there, and there, and there, and all the way up to there, right? So this is our nice continuous function, and it's a function of t. But the thing is, again, let me highlight this. This lower limit is a fixed constant. This is a variable, right? And so this upper limit, so the lower limit is fixed, the upper limit is variable. So essentially what we're going to do now, and the reason why we call it a function is because if I allow the upper limit to be a variable, I can slide it this way, I can slide it this way, and then the red region that I have highlighted here or shown here will change, right? Like if x is down here, then it would represent this area. If x is over here, it will represent this net area, right? So we define the area function, and we use a big A for area, but the area is a function of x because it depends where I put the upper limit, right? So even though my the graph here is a function of t, so the white curve is a function of t, the red area is a function of x. So the area function that we're going to define is a function of x. So define the area function a of x as follows. What does it look like? Well, I mean, we have the notation for it, right? So we're going to define a of x. We know what notation is used to represent an area or net area. It's a definite integral. The difference though is the upper limit is now going to be your variable, right? And then you're integrating f of t with respect to t, all right? Okay, so this is our definition of the area function, more precisely the net area function of the region that's bounded between the graph of y equals f of t and the t axis between the t equals a and t equals x. All right, so kind of a mouthful. It's like an alphabet soup there, but that's our area function. Let's do an example where we actually compute one of these area functions, right? So let's do that. So let's do an example and then use that example just to illustrate, not prove formally, but just to illustrate some of the properties. It's always it's always, well, there's a debate, you know, do you start with the specific and then you go to the general? Do you start with the general and then go to specifics for examples? I think both directions have merit, right? So what I'm going to do is choose a fairly simple function. Let's choose a linear function like 2t plus 1. And then let's choose the interval to be from 1, again, up to x, right? And then we're gonna, so first let's graph this function and kind of highlight the area and then see if we can come up with a nice formula, maybe using geometry, right? Because we've done that, where we can use geometry to help us solve the area problem. Maybe we can use that same approach and come up with not a specific area, but again, this area function. Okay, so let's do this. Now, recognizing that we have a linear function, really all we need are just a couple points, you know. So let's say this is 1 and then I have my x over here. Now this is a linear function with positive slope, so as t gets bigger, y gets bigger, right? So we know what it's going to look like. So let's figure out what the y value is that corresponds to t equals 1. So if I plug t equals 1 in here, I end up with a value of 3. So that's the first point on the line. If I plug x in, you're saying, oh, how do I do that? I don't know what x is. Well, again, whatever it is, we know it's going to be a value that's bigger than, well, technically it could be equal to 3 since I'm allowing for the equal sign here. But in general, if I put a value of x that's further to the right on the t-axis, then I'm going to get a y value that's higher than 3. I don't know what it is, but I can write down its expression. So if I plug x into this function, I'll get an output of 2x plus 1, right? That would be the y value that corresponds to this. So all I'm going to do is just make it representative. Has to have a positive slope, so it's going to be here, and then let's just say it continues on that way, right? And so now let's shade our area. So we have that vertical line segment, we have another vertical line segment, and I believe we've seen these before. These are, those lovely trapezoids. So we have this one, right? So we are going to write down a function, find a function that no matter what value of x I have, that function will tell me the area that I have indicated here. It's just that now I am keeping the upper limit as a variable, right? So our area function, symbolically, this is it, the integral from 1 to x of f of t dt. But this, again, I'll just say, represents the area of a trapezoid. Right? So if we can apply geometry, we can actually figure out what this area function is. We could actually find its value, right? Okay, so let's label the dimensions of our trapezoid. And as far as let me kind of remind you of the area of a trapezoid. If you have a trapezoid that looks like this, we usually use these symbols. The smaller of the two the shorter of the two parallel sides is usually labeled A, the longer B, and then that perpendicular distance between them, that shortest distance is H, and then the area is 1/2 times the sum of A and B times that perpendicular distance H, right? So we can use this formula. If you wanted to, you could split it into a rectangle and a triangle, and just, you'd have to use a couple formulas there. But this is a nice formula to remember for a trapezoid. But let's go ahead and label the necessary dimensions. All right, so this right here, this horizontal distance between 1 and x, that would represent my h, right? Well, what is that distance? Well, it's whatever x is minus 1, so it's x minus 1. What about this height here? Well, we found that specific number, right? That's 3, so that would be your a. And then the b would be this variable height, the 2x plus 1, because that's the y value that corresponds to this t value, right? So we end up having, so this is 2x plus 1. All right. So now let's use our formula for the trapezoid and actually compute this area function. So let's do it. So it's 1/2 times the sum of 3 and 2x plus 1. So that's 3 plus 2x plus 1. That's my a plus b. And then times h, which is the quantity x minus 1. And obviously now what we can do a little bit of algebra and simplify this and get a nice function, right? So let's say in the parentheses we'll have 2x plus 4 and then times that quantity. And if we distribute the 1/2, now what we're doing, technically, it's not really, it is the distributive property, but we're also using the associative property here. So we have 3 factors being multiplied: the constant, and then the first binomial, and then the second binomial. So I'm going to choose to do the product this way, where I'm going to do AB, which is 1/2 times the 2x plus 4, and then take the result of that product and multiply x minus 1. So if I distribute, so let me be clear, if I do that product, I'll have x plus 2 and then times x minus 1, expand this, and we get x squared plus x minus 2. So that's really interesting. I mean, So what this says is, so let me write it over here. We have our area function. We end up with this quadratic. So I can use this function if I were now to try to evaluate or to determine the area for different values of x. So for instance, look at what happened. Look at what would happen if x is equal to 1, right? So if I plug 1 in, I'm going to have 1 squared plus 1 minus 2. That's 2 minus 2. So that's 0. Well, what would that mean? Well, that would mean like I have a slider and I would just slide the x all the way down here. So I wouldn't have any width, to this trapezoid. And actually what would happen, it corresponds to one of our properties of the definite integral. Because if I look at this and I say, what happens if I put a 1 here? Well, we know whenever the lower limit and the upper limit are the same, the value of the definite integral has to be 0. So there's a lot here. There's the geometry, there's the property of the definite integral, and then there's the algebra of evaluating this area function, and we can see the consistency there. So we get a value of 0, right? What's interesting is, and then of course if you were to take a value of x that's bigger than 1, so let's say you wanted to know what is the area of that trapezoid when x is equal to 5. So all you'd have to do is just plug 5 in, and you'd have 5 squared plus 5 minus 2. So that will be 25 plus 5, that's 30 minus 2, so that's 28. So the area of that trapezoid would be 28. I don't need to redo this, right? This has been done generally, and now I can use the general area formula or function to find specific area values, right? Now here's kind of an interesting thing. Since we have, it's basically just a quadratic. What happens if I plug a value of x that's less than 1? What if I plug negative 1 in? Let's see what happens. So if I plug negative 1 in, so then I would have negative 1 squared plus negative 1, and then I would have minus 2. So I would end up with a negative 2 as my area. Now you'd have to remember that this is kind of a net area. So it's fine for us to get a negative value, right? It's just geometrically, it's almost like now I've taken the slider and I slid it to the left, and then I go past the 1, so now I'm over here. But it's like having 1 as the reference point. As long as your x is bigger than 1, then you'll get something positive for your area, which is like this one. When your x is equal to the lower limit, so when x is equal to 1, you'll have a net area of 0. And then when your x is less than 1, you'll have a net area that's negative. So you kind of see the possibilities here. So when you get these numbers, it's important to keep the original area in mind in terms of where is the upper limit positioned. Is it to the right? Is it at the lower limit, or is it to the left of the lower limit, right? So that's how you can evaluate it. And here's another way that you could evaluate it. So what I'm going to do is draw the figure again quickly like this. So remember we started at 1 and we went up here, and the region like always started at 1. But suppose now I wanted, so this is the same 2t plus 1. So this is the same function, 2t plus 1. But what if I wanted the area where even though the function is defined from 1, what if the region now, I decide to cut off a piece of this, and let's say I want to know the region between 2 and 4, and I want to make use of this area function, right? Well, what we can do in order to find this white area, this area that I have shaded in white, pretend for a second that you have this, right? So find the area from under this of the trapezoid from t equals 1 to t equals 4, and then, so let me write that down. So find a of 4, that's the red one, and then subtract from that the piece that I'm trying to eliminate, this part. And then that would be a of 2, right? So since I did that in blue, let me do that in blue. So a of 2. Hey, red, white, and blue. So if you do this calculation, so it's a little hard to see, but let me kind of do that. So to find that area, again, since 1 is my reference point, remember this function is defined with this constant lower limit of 1. So now find the area from t equals 1 to t equals 4, that's this, and then subtract from that the area from t equals 1 to t equals 2, and then that will leave this piece off. In fact, what we're using there is again another one of the properties of definite integrals that we looked at earlier. So what is, in fact, let me just stick with one color. I think that's enough patriotism in one video. A of 4, what's A of 4? So that will be 16 plus 4 minus 2. And then subtract, what's A of 2? So that's 4 plus 2 minus 2. And we should get something positive. Why? Because this region here between 2 and 4 is completely to the right of t equals 1, right? So we should get something positive. Let's see. So 20 minus 2, so that's 18, minus 6 minus 2, that's 4. So we end up with a value of 14, right? So, basically now I could use this nice trick of taking my area function, finding a larger area with that fixed reference point, finding a smaller area, again with the same fixed reference point, take a difference and get kind of an area with that bounded but doesn't include the region down to t equals 1. Right? So you can use it to find those kinds of areas as well. Now, again, let me kind of summarize what we've done. So let me write the original function again, 2t plus 1, and we defined an area function over that interval, and then and we did our geometry, and we came up with this nice, useful and simple formula, x squared plus x minus 2, and we did some calculations. Now, if so this in itself is another function, right? It's another function. In fact, it's a polynomial, so we know it's always continuous, and we know polynomials are also differentiable. So what if, just for fun, just for kicks, we said, what if we were to take the derivative of this function? So a prime of x, that would just be 2x plus 1. And I want you to take a look at this. So this was the function whose graph we started with. We came up with its area function, and then at the end now, we just took its derivative. So this is the derivative of the area function. Now remember what a derivative means. It's a rate of change. So this being the area function, then this is the rate of change of area. But look at how similar these two functions are. In fact, the only difference is that, again, the original function is in terms of t. That remember what we said, that the graph was a function of t, and the area is a function of x. And the rate of change of that area is the same function that defined the graph. Right? So the only difference is, so it's like basically what have we illustrated there? We've shown differentiating an area function, right, gives the original function, right? Just with a different variable. I'll put that in parentheses, with a different variable. So basically, the derivative of the area function is the original function. That means the area function would have to be an antiderivative of the original function, right? So if you think about it, when I differentiate the area, I get the original function. So that means the area function would have to be an antiderivative of the original function. Yes, because otherwise, when I differentiate the area, I wouldn't get back the original, right? So that's one important fact. And simply based on how we've defined antiderivatives, we can say this. So this implies that an area function is an antiderivative of the original function. When I say original function, the function whose graph we drew, and to define the region whose area we then computed, right? So when I say the original, I mean like my f of t here, right? So derivative of the original function. Again, look at this statement. Area is antiderivative. So it seems like for us to get a handle on solving the area problem, it looks like we're going to have to use antiderivatives in order to do so. Pretty big conceptual leap there, and I think that this is a perfect kind of place to stop. It's like a cliffhanger, so you have to tune in next time to see how this all comes together. But yes, keep that in mind. If we want to solve the area problem, we have to now look at antiderivatives. I'll see you guys in the next video.